So we have a relation on n cross n. Let's first of all think about what n cross n is before we even really start. So this is the set of all pairs of natural numbers. Um, so instead of doing it set notation here, I'm just going to give us some examples. So 1, 2 would be a member of this set. We could do 2, 1 would be a different member of the set. We could have 7, 17 would be a member of the set. We could have something and itself, 5, 5. It's sometimes helpful. So sometimes it's good to get things that aren't part of this set either. So for example, 0, 5 would not be part of that set. 0, anything would not be part of the set because 0 is not a member of the naturals. I also couldn't have a negative, so I couldn't have something like 2, -1. And it is natural, so I certainly couldn't have a fraction there also. So that's what's in this set n cross n. Now the relation itself is on n cross n. That means some element in this set is potentially related to another element in that set. So we now have 4 numbers. Each of our elements has a pairing of numbers here. And they're related if the first times the last equals the second times the third. So starting off with elements of this relation, remember, to be an element in the relation, it needs 2 elements from this set. So we might have something like 1, 2 is in relation with 5, 10, because 1 times 10 equals 2 times 5. They both equal 10. So the element itself, I mean, you could write it a couple different ways. One way would be to write 1, 2, and then a comma, and then 5, 10. And so we have an outside thing. So this itself is an element of the relation of this relation right here. Again, the relation requires 2 elements from your original set. So here would be the first element, here would be the second element. And we could do a few more. So let's do, say, 3, 3, 5, and maybe we do something like 9. Now we could even figure out what this one has to be because the 2 middle ones, the product is 45. So the outer has to have a product of 45. So that would be 3 times 15. So this would be another element of our relation. So these are 2 elements of the relation. And I know I needed 5, but I gave some others on the homework. So proving it, remember equivalence relation, we need RST, reflexive, symmetric, transitive. So reflexive, we're going to pull any possible element from this set right here. So I'll just do R for reflexive. Let AB be a member of n cross n. So we're going to pull an arbitrary element from our original set. Then we know this is true because the outers, a times b, equal the inners, b times a. I mean, with natural numbers, they're commutative. Doesn't matter what order you multiply them in. And so we know that any element that we choose in n cross n is going to be in relation with itself because it's going to fit this property right up here. So this gives us reflexive. Now symmetric, we're going to have to choose 2 arbitrary points. Let A, B, and C, D exist in n cross n. So reflexive, you always choose 1 arbitrary point from your set. Symmetric, you choose 2, and transitive, you're going to have 3, such that the first relates to the second relates to the first. So then we want to show basically that, and we can even set it up. We can go ahead and assume such that AB is in relation with CD. So we need to show, and sometimes people do WWT, we want to show that. WWTST. If you want to abbreviate here, not much of a writer, you could use that. We need to show that the second element, CD, is in relation with AB. Notice that we don't reverse the order within here. We don't say DC. The element we chose was CD, and so we still want that element. We just want that element to come first. Well, since this is true, we know that AD equals BC. We also know that CB equals DA, right? Because here we just reversing the order, and then whether it's left side or right side of the equation, that's not matter. If this is true, then this has to be true. So here we've just shown symmetry, because since this is true, we know that this is true, and that tells us that C times B equals D times A, which means that this element is in relation with this element here. So here we have symmetric. If AB is related to CD, then we can flip it and say CD is related to AB. And finally, transitive, so that AB, CD, EF exist in n cross n such that AB is in relation with CD, and CD is in relation with EF. So here we want to take stock of what we have and what we need to show. Well, since this is true, and I'm going to do this visually instead of writing it out, so that I think that'll give a better sense of what's going on here. Since this is true, we know that AD has to equal BC. And since this is true, we know that CF equals DE. We're assuming that these two things are true. This is part of our assumption. And what we really need to show is that AB is in relation with EF. So I'm going to say we want to show that AB is in relation with EF. Now this would be equivalent to saying that if we could show that AF equals BE, we'd be done. So it'd be nice if there was a real quick substitution, but we're not seeing that. So we look, maybe we can solve for, if we want to get AF, maybe we can figure out what F is, for example. There's several different ways we could do it at this point. Actually, let's solve for C, and then we can plug it in here. So here, C would equal AD over B as long as B is not equal to 0. Otherwise, this would not be true because we can't divide by 0. So if that's true, then we can take ADF over B. And what we're doing here is we're taking this equation, and we know that C equals AD over B, so we're plugging in AD over B there. And we know that this equals DE. Okay, well this is close because we have an AF over here. Let's divide both sides by D. So that would give us AF over B equals E. And again, in order to divide by D, we have to put in that clause that d cannot equal 0. But once we get this, we're really close to what we want to achieve. We multiply both sides by b. So this would prove transitive if b is not equal to 0 and if d is not equal to 0. Well, are b and e equal to 0? Well, they couldn't be, right? Because b and e both have to be from the natural numbers. So we know that those will not be equal to 0. So then all the steps we did here are valid. And this is a transitive relation. And that's why this relation is an equivalence. So we have reflexive, symmetric, and transitive. And then 5 members of the class 3, 4. So if we want to be in 3, 4, let's just take, I don't know, let's take 9, for example. We know that the 9 times the 4, 36, has to give us 3 times some number, which would be 12. So 9, 12 would be in the same equivalence class. We could also do 6, 8. We could do 30, 40. There'd be several examples there, as long as it follows this rule right here. For D, some examples might be 4, 10, 20, 50. I know I'm not listing out 5, but really the point is if the two numbers would reduce to 2/5, so 20 divided by 50 is the same as 2 divided by 5, then it's going to be part of this equivalence class. Okay, and then the reason that is because this symbol is really setting up fractions and equivalent fractions, the positive rational numbers. So if a over b equals c over d, so if you have two fractions that are equivalent, like 1/2 and 5/10, or 10/12 and 5/6, we've all remember like fractions, putting them in lowest terms. We're trying to get up equivalent fractions. So if two fractions are equivalent, or in fact, let me make it a little stronger. If and only if, and here's where we would say a, b is in relation with c, d. And we can even see this mathematically. A times d equals b times c. That's the same as cross multiplying here. A times d equals b times c. So basically, to be in the same equivalence class, you have to be an equivalent fraction if you put one number over the second. So that's the connection there. On F, the reason that it doesn't hold if we allow the numbers to be coming from the integers is precisely because of these two claims here. So in order for the transitive step, now these two steps I think would work out. Yeah, the reflexive and symmetric would work out for z cross z. But as soon as we try, let's try to do something where b is 0. So let's say a is 2 and b is 0. And then we might have something like, I don't know, let's take 5 and 0, for example. So here we do have 0 times 5 equals 0 times 2. So it does meet this condition. So this element here would be in z cross z, but then when we try to set it up as a fraction, it doesn't have this same connection with the rationals because we can't have 2 divided by 0. You can't have 0 on the bottom of a fraction. Similarly, you can't have 5 divided by 0. So we wouldn't have this relationship with all fractions. We would as long as b or d aren't 0. So we could maybe adjust this somewhat. But if it was allowed to be any integer, it would fail the transitive property. And that's why we would not have an equivalence relationship if it was on z cross z.